design variable is the storage size of the intermediate energy storage size. And the last one is, of course, the flow rates of the X productions. So for designing the PTX systems, so for designing the PTX systems, which finds the optimal design variables to minimize the production cost or some other performance, the previous studies have assumed to use the fixed period renewable profiles, ignoring the uncertainty of the profile data itself. So for suggesting some reliable decision point or design point, considering the time series uncertainty of the renewable profiles is important to prevent the oversized problems and secure the economic feasibilities. So in these studies, we adopt the reliability-based design optimization approach, which is called the RBDO. The optimization goal of these studies is to try to figuring out the optimal design variables, which can reduce the impacts of the renewable uncertainty to our objective functions, which is the production cost, and while regulating the constraints of the performance of the renewable performance of the PTX systems, which should be defined in the probability density domain. So for implementation of the RBDO of the PTX designs, two sections are considered as the workflows. In the first, regarding the construction of the PTX evaluation models, the model calculate the distribution of the production cost and the grid penetrations under the impacts of the renewable profile uncertainty. To complete the first work, firstly, the uncertainty modeling of the renewable profiles was conducted based on the data-driven approach. And the second, under the given renewable profiles and the design variables, power allocation model was formulated to calculate our target outputs. And in the second section of the RBDO, in RBDO, the constructed PTX evaluation models was properly integrated with the additional stochastic simulators and conventional derivative-free optimizers to figuring out some reliable design points. So in the first section for the constructing the PTX evaluation models, we adopt the generative adversarial network approach to modeling the uncertainty of the renewable profiles, which is called the GAN. So during the training, the noise sample from the Gaussians transferred to the generative network, and the network produced the fake annual profiles of the wind and solar. At the same time, in the discriminate network, the real wind and solar profiles was driven from the database and transferred to the discriminator with the fake generated data. So using these two data in discriminators, the network tries to measure the difference of the distribution between the real and the solar. So after the training, the generator can theoretically capture the temporal dynamics and some complex patterns of the historical data. And using the trained generator, we can generate the distribution of the renewable profiles from the simple noise Gaussian vectors. For the training, the GAN, the Jeju Island in Korea was chosen for the geographical sites, and the data, we download data from the 2001 to 2019, and the data types are the wind and the solar irradiations. And all of the data was automatically downloaded from the NASA Renewable Power Data Bank API. The detailed network structure and the loss functions are as follows. In the training, to capture the temporal dynamics of the historical data, the deconvolutional layer and the convolutional layers are included in the generator and the discriminator network respectively. For the training, we adopt the Adam optimizer and the training batch size of the real historical data transferred to the discriminate network in the every iterations, and the total 1,000 epoch is conducted. As I mentioned, in the terms of the generator, it is important to generate the fake data, which has a very close distributions to the real one. And in the GAN, to measure this performance, we can use this Wasserstein laws, which is calculated by these equations. And this equation means that how much fake data is close to the real ones. And as you can see in the training graph, both in wind and solar case, epoch are going on, and this distance between the fake and the reals going decrease and goes to near zero. And the second step for constructing the PTX evaluation model is formulating the power allocation models. In the model determines the under the given profiles and design variables, the model determines the time series profile of the renewable and grid allocations to the subsystems in the PTX systems. The power allocation case can be classified to the major three cases. In the first case, after the generated renewable powers transferred to the electrolyzers, and the electrolyzers produce the hydrogens, and also a portion of the renewable powers transferred to the X production systems. For example, we capture CO2 and produce the methanol or some high value of chemical. In these cases, surplus renewable powers transferred to the storage tank and converted into compressed hydrogen gas. And the second step is that if the renewable power is insufficient for operating the electrolyzers, in this case, the additional power is supplied from the power grid, and the additional hydrogen is feed from the storage tank for the constant X production. And the last case is when the renewable profile is insufficient for operating this X production system. In this case, the renewable power directly sent to the X production processes for operating without passing the electrolyzer or the storage tank. And also grid power supplied additional power to the electrolyzers and also to the X production systems. And also additional hydrogen is supplied from the storage tank. So the constant X production was accomplished. So due to this well-defined case of the power allocation, even though I said this is the mathematical models, but the power allocation models can be constructed by using the simple energy balance and mass balance and energy conversion efficiency, which is driven from the Aspen plus. And this is the examples of how we defined and construct the power allocation models in the Python environment. So using the train generator and the power allocation models, we can construct the PTX evaluation models. In the models, noise vector sampled from the Gaussian distributions, let's say like 1,000 samples is 1,000 point is sampled from the Gaussians, and the sample point transferred to the pre-trained generators and generate the n cases of the renewable profiles. And using these n cases renewable profiles with the design variables, we can calculate our target outputs, which is the production cost and the grid penetrations in each cases. According to these procedures, we can calculate the distribution of the production cost and the grid penetrations under the given design variables with just a simple noise point. As mentioned before, using the PTX evaluation models, we additionally conducted the reliability-based design optimizations to figuring out some reliable design points. But in the RBD approach, due to the probabilistic behavior of the system, two different points are encountered compared with the conventional optimization problems. The first one is the constraint. In the RBD approach, for calculating the constraint, of course, firstly, we should have to define the limits about the constraint. In this case, we assume that the grade penetration as a constraint, so that we set the upper limits about here. And as I repeated again, because due to the uncertainty impacts, the grid penetration of the PTX also follows the probabilistic distributions. So grid penetration points which beyond our upper limits can be defined as the failure points of the system. And this is just a semantic definition about the failure, and it does not mean that really the process is the fail or something. So just remind it. So if we, and according to these definitions, if we know some exact information about the distribution of these grid penetrations, we can calculate the probability of the failure of the systems. And the second point is the objective functions. In case of the objective functions in RBD approach, two objective functions are considered, which is the mean and the variance of the production cost. And according to minimize both objective functions tries to minimize the overall distribution of the production cost itself. So according to this perspective, in RBD approach, the objective and the constraints can be assumed as follows. But in case of the calculating the constraint, which is the probability of the failure, it needs additional stochastic simulator techniques. Of course, if our model is simple, linear, and low computational cost, we can just use the simple Monte Carlo simulation to calculate this failure probability. But in case of our PTX evaluation models, it has a high dimension about the uncertainty, and the PTX model itself has a high nonlinearity. So Monte Carlo simulation approach is not a good, it's not a feasible options. So in these studies, we adapt the subset simulation stochastic methods. The basic idea about the subset simulation is define our target failure to the products of the sequence of conditional probability, which can be derived from the subset points. So in here, let's say that our target failure domain is in here, which threshold is zeros. And from the initial subset, using the subset as a random sampling, we can generate the next subset which satisfies these conditions. And according to the algorithms about the subset simulations, we can continuously decrease the threshold and calculate the failure of the probability with the high addresses. So according to the two techniques, we formulate the framework. And as you can see in the graph, all the optimal points are satisfied our constraint. And because we adopted two objective functions, so as you can see in the graph, the production cost has a trade-off relationship between the average value and production value. And this is the uncertainty propagation results about these three representative points. As you can see in the graph, the variations are generally continuously decreased. So this is the conclusion of our research, and thank you for listening. And the funding was supported by the development and application of the carbon neutral envelope platform. Thank you for listening.
Very much. Questions for the speaker?
One question which is related to the design. Do you have an idea of how the design has been changed to the decisions, size of equipment, when you account for those uncertainties?
Yeah.
do you take other decisions, or is the design not
actually-
necessarily affected? Just,
If I understand your questions, in these studies, we only consider about the three variables that I presented.
Yeah.
And actually, this is some initial step of the work to considering the uncertainty in the design of the PTX system. So maybe at the further studies, we can incorporate the operation conditions or more details, the condition as the decision variables in here.
Yeah, but you decide the volumes.
Yeah. Yeah.
And the electrolyzer. So do you take different decisions? Or is the electrolyzer bigger when you account for the uncertainties than if you don't, for example?
You mean the compare the results when considering the uncertainty or not?
Yeah.
Actually, we haven't tested that yet, but that's a very good feedback. So maybe after return to Korea, maybe I can add some results, and it's really good to qualify our work. Yeah.
Okay, maybe I'll ask a quick question. So how many samples do you actually use for this?
First, to calculate our objective functions, the 1,000 samples are generated from the noise. And as I said before, to calculate the failure probability, the more samples are required to meet the high accuracies. So in this case, we just adaptively sampling using the subset simulation methods. But in this case, we did not track how many samples are required in every different decision points, but maybe it could be also add in the next figure or something to illustrate how effectively it reduced the sampling point percent. Anyway, the 1,000 sample kits.
So let's thank the speaker for this presentation.